Welcome to today's Explainer. I'm honestly so incredibly excited to walk you through this material today because right now we are looking at a massive evolutionary shift in the world of autonomous coding agents. We're finally moving past the days of basic code completion tools and stepping into an era where AI can handle entire software lifecycles. But as you'll see, that massive leap forward comes with a very specific, very frustrating set of growing pains.
So I want you to picture this. What happens when your AI coding agent gets stuck in an infinite loop at 3 a.m.? You set up this highly capable agent to refactor a massive codebase overnight. You go to sleep expecting a neatly wrapped pull request in the morning, but instead, you wake up to find that the agent hit an unexpected environment error, panics, and then spent the next 6 hours endlessly repeating the exact same failed command. It just burns right through your API credits. It's a painful, expensive reality, and solving it? Well, that is the holy grail of modern AI engineering right now.
Okay, let's dive into this. Here is our roadmap for how new models are solving these exact bottlenecks. 1. The autonomous coding bottleneck. 2. Worker versus the contractor. 3. Mastering loop resistance. 4. Safeguarding agentic long horizons. And 5. The new engineering frontier.
Section 1. The autonomous coding bottleneck, agitating the pain of long sessions.
To unpack exactly why these 3 a.m. disasters keep happening with older generation models, we really need to look at our biggest culprit here, context rot. You see, when an AI agent runs autonomously, it has a finite memory buffer, its context window. A highly verbose model, one that feels the need to explain every single step it takes, fills up that window incredibly fast. As that session extends, the model essentially starts to lose the thread. It forgets earlier instructions, it drops variables, and its reasoning begins to noticeably degrade. Or it's forced to constantly reset its context, completely losing the overarching shape of the project.
And you can totally see why this is a problem when you look at how these agents actually work. They operate by chaining tools in a continuous loop. They read a file, write a code change, run the tests, interpret that output, and then repeat the whole thing. In this constant loop, token inefficiency compounds heavily. If an agent isn't absolutely concise, every iteration adds unnecessary bloat. That bloat directly accelerates context rot, pushing the agent closer and closer to that dreaded state of confusion where it just starts spinning its wheels.
Section 2. Worker versus the contractor, the shift in AI paradigms. There is a brilliant metaphor from the sources to anchor this. Think of older models or your standard coding assistants as the construction worker. They type the code you explicitly tell them to type, and they usually work on one isolated file at a time. But on the flip side, we have the contractor. This is the true product manager agent. Contractor models, like the newly released Claude Opus 4.7, don't just write code, they run the entire build autonomously. They manage the UI, the API, the database, the deployment, the whole shebang. They understand why something is failing and where the fix needs to land across a massive project, rather than just treating every step as a disconnected puzzle.
Section 3. Mastering loop resistance, surviving the infinite loop.
This quote from Kate Schuh, the CTO at Genspark, really hits the nail on the head when it comes to production reality. During early testing of Opus 4.7, he noted that loop resistance is the definitive differentiator. I mean, think about it. If a model loops indefinitely on even just 1 out of every 18 queries, it becomes fundamentally unreliable. It wastes a massive amount of compute and totally blocks the user. For enterprise teams, you need that loop resistance because lower variance in execution means way fewer nasty surprises in production.
Let's move to and see how this builds out in practice. How do these frontier models actually resist loops? Well, robustness in long horizon tasks isn't about getting everything perfectly right on the first try. It's about recovery. The sources point out 3 concrete steps. First, they interpret local execution feedback correctly, even when it's super ambiguous. Second, they actively avoid repeating the failing action. It's like they realize the door is locked and they stop trying to push it open. And third, absolutely crucial here, they reset the relevant state files and find an alternative path without losing the context of the overall task. That's what prevents a minor hiccup from compounding into a total failure.
So how do the top models stack up right now? If we look at the current frontier, we see a really fascinating divergence in strengths. GPT 5.5 is emerging as the terminal first champion. Because of its highly structured tool use and just incredible token efficiency, it handles agentic loops brilliantly for DevOps and shell execution tasks. It generates less narrative overhead. But then we have Claude Opus 4.7, which is the codebase first leader. It excels in sustained reasoning over complex architectures, holding onto a coherent map of massive projects for high-level PR reviews and those super intricate coding sessions. 2 different approaches, both incredibly powerful.
Section 4.
safeguarding agentic long horizons, controlling the autonomous agent.
Now take a look at this number, 1.0x to 1.35x. This is the token multiplier for the new Opus 4.7 tokenizer compared to its predecessor. While this new tokenizer dramatically improves the model's accuracy, the trade-off is density. The exact same Python function might cost up to 35% more tokens to process. Better reasoning and stronger loop resistance often require the model to think more at higher effort levels, and, you guessed it, more tokens mean higher costs.
So, the million-dollar question is, how do we control this? The answer is a brilliant new beta feature called task budgets. This allows you to set a hard token ceiling on an agentic loop. The model actually sees a running countdown of its remaining budget. So instead of just abruptly cutting off mid-task when funds run out, it uses that countdown to prioritize its work and finish gracefully. For any team running those overnight autonomous coding runs, this is literally the feature that solves that 3 a.m. cost control nightmare we talked about earlier.
But it's not just about API limits, right? It's also about how we train and evaluate these agents to be robust in the first place. That brings us to Claude Gym. This is a highly scalable framework designed specifically for building effective personal agents. It synthesizes over 13,000 diverse tasks, drops them into realistic mock workspace environments, and then judges the agent's performance using hybrid verification. It checks objective code execution and qualitative rules. Essentially, it forces the agent to learn true resilience in messy local file systems.
And a really cool piece of the Claude Gym framework is the sandbox parallel rollout. Because these agents are operating over such long horizons, training them requires vast amounts of interaction data. This pipeline takes every task and virtualizes it into its own completely independent sandbox. It gets its own root file system, its own verifier. This lets developers evaluate and train thousands of agents concurrently, without them bumping into each other or interfering with each other's environments. It's the exact infrastructure needed to create these robust, loop-resistant agents at scale.
Section 5. The new engineering frontier, the benchmark receipts.
And this brilliantly illustrates the leap we've just taken. Looking at the OS World Verified benchmark, which tests an agent's ability to complete open-ended tasks in real computer environments, Claude Opus 4.7 pushed performance all the way up to 78%. This isn't just because of better text reasoning. It's a combination of that critical loop resistance we discussed, plus a massive 3.3x increase in vision resolution. The agent can now clearly read dense UIs, architecture diagrams, and high-res codebase screenshots. It navigates systems almost exactly like a human engineer would.
Which brings us to a fascinating, maybe even slightly daunting final thought. As these frontier models shift from being junior workers that need constant supervision to autonomous contractors that manage their own task budgets, recover from their own errors, and actually avoid their own infinite loops, what happens to the human orchestrator? We're no longer just coding, we're managing parallel teams of digital agents. The bottleneck is no longer the machine's ability to code. The bottleneck is now our ability to dream up the architecture for them to build. Thanks so much for joining me on this explainer, and I will see you next time as we continue to unpack the frontier of technology.